Okay, so hi to everyone. Thank you for coming along to ASEG New South Wales April meeting. Thank you to our in-person audience, thoroughly enjoying pizzas and beer, and our online audience as well. Wow. So just a few housekeeping slides. And it's not going. Oh, there we go. Okay, so the ASEG acknowledges the traditional owners of the land on which we gather today and the many lands on which we undertake our work. We recognise their continuing connection to these lands, water and culture, and pay our respects to their elders past and present. So a big thank you to our corporate members and to our branch sponsors. If anyone wants to sponsor the New South Wales branch, get in contact with me or any of us on the committee. So for our friends on Zoom, if you have a question, click on the Q&A function and the moderator will see that you have a question and then type it in and we'll address them after the presentation. And if you're not a member of the ASEG, please do become one. We had the AEGC conference was it last month? And you get a subsidized cost for that. And we do have our dinner in New South Wales coming up soon. So again, that will be subsidized. And keep in touch on all the social medias. And now we'll go here. Okay, so Jaime or Jamie is a professional astronomer. Is a professional astronomer originally from Colombia. He is a PhD candidate at Macquarie University and is passionate about computing techniques, software skills, writing and learning about science and its constant evolution. Jamie's research field is the planetary sciences, emphasizing extrasolar planets, moons, rings, asteroids, and comets. Most of Jamie's work is about how extrasolar systems evolve. Studying such systems can give us valuable information about their formation. It can help us understand more about the history of our own solar system. Currently, Jamie is in the last 3 months of his PhD. Good luck. He plans on continuing his career in academia as a postdoctoral research fellow, since his ultimate goal is to become a full-time researcher and professor. So we welcome Jamie.
Hi, everyone. So today I'm going to talk about the James Webb Space Telescope, this new telescope in space that's going to help us discover many things that we haven't been able to do yet because we didn't have the technology for it, right? So the talk is titled Unveiling New Horizons of the Cosmos with the James Webb Space Telescope, okay? Now, before proceeding with the talk, I would like to thank you for allowing me to give this talk here at the ASEG. Also, throughout this presentation, I'm going to be using images and results from the JWST project. And most of the credits go to NASA, ESA, right? So this is the European Space Agency, Canadian Space Agency, the BBC, and the project scientists of JWST from ESA, right? So, well, let's get into the topic. So 3 important facts about JWST is that this is a joint mission between NASA, ESA, and the Canadian Space Agency. Now, this is the first time, right, that we have such a big telescope. This telescope is huge, you will see in a minute, and it's an infrared observatory, right? So this is very important because so far the only like good infrared telescope that we had in space was the Spitzer telescope. I will show you in a minute. But the problem is that there was a region of the spectrum, of the electromagnetic spectrum, that we couldn't observe, and now we can because we have the JWST. Okay, now this telescope will extend, right, the resolution and the spectrum coverage of the Hubble Space Telescope. The Hubble, I guess most people know what the Hubble is. It's a telescope put in orbit in 1993, right? and it's been there for a long time, for a very, very long time, for 30 years. Right? And we have discovered many things with the Hubble Space Telescope. Now, when we compare, we will do that in a minute, the Hubble with the James Webb, you will see how now things are way, way better than the Hubble, and the Hubble was great. So Webb was formerly known as the Next Generation Space Telescope, and it was renamed in 2002 after the former NASA administrator James Webb. And I put that name in red because at the end of the talk, I'm gonna refer to this guy again, and because there is a bit of a discussion about changing the name of the telescope because of some issues, and I think those issues should be addressed too. And it is often called the next big step after the Hubble Space Telescope. Basically, it's a very like a big leap forward towards discovering new things in the universe. Right now, James Webb. Here is a basic comparison of the main mirror. James Webb has 3 mirrors. A primary mirror is 6.5 meters in diameter, but it's so big that, well, we can, but it's not practical to put such a big mirror into space, right? So basically, these 6.5 meters are divided into 18 hexagonal segments, right? These bits. Each of them, right, is made of beryllium and coated with gold. Now, this is the size of the Hubble primary mirror, so you can see the big difference between them. Here, there's some basic facts about the James Webb and the Hubble, right? So the launch of the James Webb was in 2021. So that was on the 25th of December 2021. And the Hubble was launched in the 1990s, right? So it's been in orbit for 32 years. It's a long time. And the expected time for the James Webb to be in orbit is going to be around 10 years. It was originally 5 years, but the launch of the telescope was so perfect and we didn't run into any problems. And the rocket that we used, the Ariane 5, so the rocket from SpaceX, did such a good job that the propellant that we needed was kind of like we had more propellant that we needed. So now we have the original time, the original lifetime for the James Webb was 5 years, but thanks to that the launch was so perfect, now we have a lifetime of 10 years or possibly more than 10 years. Could be 13, could be 15 years. Some say that it could be even 20 years, which would be amazing having this telescope for that long. Now, of these facts here, the most interesting thing and what makes the James Webb special is this, the operating temperature. Look the difference between both of them. The operating temperature of the Hubble is 20 Celsius degrees, but the operating temperature of the James Webb is minus 230. That's what makes it special. That's what makes it good. This temperature allows us to observe in the infrared, observe in this region of the electromagnetic spectrum that we couldn't do before, just because this is too hot to observe there, right? So if you have a telescope that is at this temperature, that temperature will affect the electronics of the telescope, and the electronics, the heat that starts like emanating, right, radiating from the electronics, it will get to the mirror, it will get to the detectors, and then it will mess up with the data that we collect from the stars, the galaxies, and clouds, and etc. Right? So, and if you have that into your data, then removing that it's going to be very complicated, and the images are not going to be good. So that region of the electromagnetic spectrum was kind of lost, right? We didn't have access to it. Now, very expensive telescope, super expensive, right? It's actually the most expensive spacecraft that we have put in orbit, right? And you can put actually like 3 or 4 telescopes together and it's still more expensive than them. It's super expensive, it was almost $11 billion, right? You see. And here it's like a nice comparison. It says that it's like taking all of the population from America, right? And having like $33 per American. Right, so that's what the James Webb costed, right? So a nice gift, gift for knowledge, right? And Merry Christmas from science, because it was launched on the 25th of December 2021. Right now, this is an overview of the JWST mission. Basically, there are 4 parts or 4 modules of the James Webb that are important or relevant. The telescope has tons of things. right? Tons of has 4 detectors. Well, we will get that into that in a minute. But these 4 modules, right, summarize the whole thing. So we have the telescope. We have 4 optical elements, only 2 visible here. Those optical elements are the 2 mirrors, right? So we have the secondary mirror, right? Is this one here. You can see it really. It's just there. It's very big. It's 0.75 meters in diameter, right? So it's considerably big. Now, this one is 6.5. Now, it's interesting because because you have such a big structure when it was launched, we couldn't send it just already completely unfolded, right? We had to fold it, and to put it into the rocket, we had to put everything together, right? And that's a very big advantage of having these segments, right? That allows you to fold the telescope and then put it into a rocket and then send it into orbit. Now, what else do we have here? So we have the payload module. The payload module has the 4 instruments. The 4 instruments are the 4 detectors, right? So the 4 infrared detectors, and we will get that into 2 or 3 slides. Now, this one here, that is the spacecraft bus and the solar panels. The solar panels also is one of the most important structures in the telescope because it allows to charge the battery of the telescope, right? And to keep it in orbit. Now you will see why we need that, because this telescope is in a special orbit. It's not around the Earth like the Hubble, right? So we need, the telescope needs constant energy, right? And that energy comes from the sun, and that's why we need solar panels, right? So we can keep it in orbit. Now, the sun shield is 5 membranes of Kapton foil, allowing the passive cooling of the telescope and getting down to minus 40K or minus 233 Celsius degrees, right? And it's the size of a tennis ball. So the size of the sun shield is pretty big, right? It's huge. Now, let's move here. As I said before, the James Webb mission is a joint effort between NASA, the ESA, and CSA, or the Canadian Space Agency. And this is kind of like a diagram where you can see which parts were contributed by each agency. Right? So most of it is NASA, right? Of course, NASA is actually the leader of the mission. Of the 3 agencies, NASA is the lead agency, right? And here you have that the launch segment, right? The payload adapter, the launcher, which is the rocket, right? The Ariane 5, that's the rocket. And the launch site services, all of this was provided by the ESA, right? And Europe, well, the European Space Agency. And here only this is a detector. This is a detector. This is called the slitless spectrograph. So it's a spectrograph without a slit. And this was provided by the Canadian Space Agency. And this another detector, half between NASA and ESA. And most of the other parts, the spacecraft bus, the telescope, the NIRCam detector, the common systems, the deep space network, that is basically what we use to collect the data, to receive the images and everything. And the Science and Operations Center, right, that is here on Earth. All of that was provided by NASA. Now, because we have a mirror that is indeed not a mirror, a big mirror, right? It's just like the superposition of different segments. Then we need to use something that is called adaptive optics. All right, this allows us to do what is happening right there. Right, if you have like the contribution from all of the segments. Now each of them has 6. We could call them engines. They call them actuators, and they allow to move each segment in 6 degrees of freedom. Right, so they allow you to move in X, Y position, piston, tip, tilt, and clocking. And they also have an engine. Each of them, each segment has an engine that allows the curvature of the segment to be deformed. Right, all of that just to build an image that is focused and that is good quality. Right, now you can see here, this is a small like animation, right, of how the BSF of a star is built using the contribution from all of them. So you can see that once all of them hit the secondary mirror, then you have the image, then you have the information that gets to the primary mirror. Well, from the primary mirror to the secondary mirror, and from the secondary mirror down to the instruments, down to the detectors, right? And that's once the light goes from the secondary mirror down, that's when, depending on the program that we're working on, right, or the instrument that we're using, then maybe we could be observing galaxies, planets, or stars, etc. Right? So depending on what the program is. Now, something that I haven't mentioned yet is that this is a general observatory. They call it like that. That means that it can be used by anyone with a good science program, right? If you have a good science program and you can justify it, and you have like let's say like a good design of what you're going to observe and what you're going to do, they will give you the time, right? They will give you the time. But of course, it's super difficult to get time on this telescope. It's a space telescope, it's super expensive, so not any program gets through, right? But in theory, like anyone could propose something to observe with the James Webb. Now, this is a summary of the JWST deployment, right? So JWST completely folded inside the fairing of the Ariane 5 rocket. So here, there it is. That is the space telescope. That's the James Webb, right? It's inside that rocket. So such a big thing, and it's inside that, right? So that's amazing. Now you can see that during the first month, it was the unfolding of the sun shield. That took 1 month to do, right? And actually during the first 6 months was like getting ready the telescope. During the first 6 months, no data was taken, just was getting it ready for observations. And everything worked nicely, like no problems at all. After we have started observing, we started having problems, right? I will talk about that later, but yeah, we had a big problem, something that could have been very bad, but it wasn't. Like, thankfully it wasn't, and it's still in orbit and we're still observing, right? So basically this whole thing, until the telescope was ready for observations, took 6 months, right? Now, this is something that I was mentioning before, right? And these are like an example of 4 different observatories, right? So you have the Hubble Space Telescope, the James Webb, the Spitzer Space Telescope, and the Atacama Large Millimeter. Of these 4, these 3 are space telescope. This one is not, right? This one is ALMA, the Atacama Large Millimeters Array. We call it ALMA, and that is in Chile. So this is a ground-based telescope using interferometry, right? So, but you can see the most important part of this is the region of the electromagnetic spectrum that they cover. All right. So before JWST, if you remove the JWST from this image, you see that this whole region from here to here was lost. We could observe. We didn't have any instrument to observe that region. Right? Now, the Hubble Space Telescope is the highest sensitivity of the Hubble Space Telescope is in the ultraviolet and in the visible. So you can see that the Hubble covers completely the whole visible spectrum, and it overlaps a bit with the James Webb, a little bit, right? So the James Webb has also instruments that can observe in the visible, but that's not what James Webb was made for. Right? The James Webb was made for this region that we couldn't observe. Now, the Spitzer telescope has also a bit of an overlap, right, with the James Webb. Now, the difference is that, for instance, if you grab this bit of the electromagnetic spectrum, you might think, okay, well, the Spitzer telescope was already covering that. But the difference is the size, right? The James Webb is much larger, way larger, right? Therefore, the images they have better resolution. And you have better images just because the mirror is way bigger, right? Now, well, this is just there for illustration, but this is already like the far infrared, right? And that's what I meant before, that we needed this instrument, that this was something necessary. Actually, this telescope, the idea of this telescope came out in 1996, right? This took time, right? It was planned for 2007. Like, we thought that we were going to be ready in 2007 to put it in orbit, and took until 2023. So imagine, it was a delay of 16 years, right? Lots of things, right? Actually, when the telescope was already kind of like ready to be in orbit, that was in March 20 of 2020, but then pandemic, right? Then COVID, and then of course we couldn't put it in orbit. We had to wait more than 1 year to put in orbit in 2021, the 25th of December, right? So there's been a lot of problems on the way. Now, at the beginning, the program, the JWST mission, wasn't that ambitious. It wasn't going to be so expensive, right? But it got that expensive, and the program got so delayed because of the broadening of the program, right? Like more people started thinking about all the things that could be done with the JWST. So, oh, why don't we do this and that and this? And then, of course, the program just expanded so much that we couldn't do it from 1996 to 2007. That is just, what is that? Like 11 years, right? So it took more than that, right? It took a lot of time, right? So 27 years. So no, 25 years, right? Now, so with that, like, I can leave it that infrared astronomy is the key tool that the JWST will use to discover new things. That is the thing, and all of the images that we're going to be like seeing here, and all the images that the JWST is going to be taking are in the infrared, right? All of the images are in the infrared. Many of them are like the colors that you will see, and are like artificial colors that are like just to enhance the little things that are in the images, right? Like clouds or auroras or rings and all of these things, because in the infrared, well, we can't see in the infrared, right? Like we can't observe heat, right? But then we need to convert that heat into other colors, and then we are able to see, right? Now, these are the state-of-the-art infrared detectors of JWST, right? So this is the near infrared spectrograph, right? This is the near infrared camera. This is the mid-infrared instrument. This is the fine guidance sensor, and this is, I think, in my opinion, like one of the weirdest ones that JWST has, and it's called the near-infrared slitless spectrograph. So it's a spectrograph without a slit, right? Now, all of them have different fields of view. Like field of view is what you can observe with your instrument, right? So all of them, they're not pointing in the same way, right? They have different programs. So actually, it's very interesting because there is a proposal, there is like an ongoing work to be able to use them at the same time. For instance, if you're pointing with JWST over there, you might be using only one of the instruments, but it could be possible to use two of them at the same time, or three of them for different programs, right? Because they use different parts of the spectrum, right? So for instance, if you're observing with this one, you're studying the near infrared, but if you're observing with this, you're studying the mid infrared, right? So you will see different structures, right? Different things in the images. Now, these are some like a general description of the instruments, of the 4 instruments. Now, what is important here is the coverage. So you can see that the mid-infrared will cover from 5 to 27 microns. This from 2.5 to 5 microns, 0.6 to 5.3, and 0.9 to 5, right? Some of them overlap a bit, and you can see here, these squares here, that is the region that is covered by each of these instruments, right? Now, these instruments, especially this one is very nice because this one is able to convert the images from infrared to light or to images that we can see. So it's the only one from all of them that can do that, right? So it takes the images in infrared and then it converts the images to visible light, to light that we can interpret. And it's the only one that can do that, right? Now, these are the fields of view. So it says field of view. So this is what the instrument can see on sky, right? So you can see that the field of view, the biggest field of view is the one from near spec. So from this one, that's the field of view of that. So all of these squares are the same in all of them. It's just the one that belongs to the instrument is the one that is highlighted, right? So this one, this bit, the smallest field of view is the one of the near infrared camera, and this is the near cam. Near cam is actually 2, right? It's 2 instruments. It's just that they're exactly the same, right? So it's this one and this one here, and this one is the biggest one. The near spec instrument has the biggest field of view, right? So most of the programs are so far, well, like we still have a lot of time and there's a lot of proposals, but so far, most of the programs, most of the things that we are proposing to do with JWST have to do with this instrument, with the near spec, right? Now, the web science. So given all of these characteristics, right, given all of these things that we can do now that we can have access to these regions of the electromagnetic spectrum that we didn't have before, we didn't have access to that before. Now, what is the science that we can do, right? So that's when things start getting a bit more interesting. So we basically, the program, the JWST is divided into 4 different categories, right? So one of the categories is early universe. So we want to study like the first stars and the first galaxies that were formed. That's one of the actually, I think was one of the most important ones because it will like give us some hints and it will shed some light on the processes that we don't know about the Big Bang, right? If we're able to observe like back in the history of the universe, then we will be able to refine and to improve some things that are still not clear, right? About the Big Bang and other theories too, right? So that's one of the programs, Early Universe. Another program is the how galaxies and black holes form and evolve, right? This is another bit that we also need like more understanding, and JWST will give us that. So it's one program, this one is the life cycle of stars. So basically here, we know, like, let's say that we've been studying stars for a very long time, and we know how stars evolve, but there's some bits of stellar evolution. For instance, like there is something that we call the genes criterion, right? And the collapse, like we said that, okay, stars form from a big cloud of gas, right? And dust, boom, huge. And then suddenly when that gas either completely globally or locally, like overpasses a limit, something that we call the genes limit, the cloud collapses. And that's when a star is formed, right? But we don't know how that happens. We haven't been able to observe that, right? That's a theory, and it works on paper, and it works with the observations that we have of stars. With all the images that we have of stars, we've been able to trace and to build diagrams, right, of how stars evolve. But the very, very first part of when a star is born, something that we call the protostars, right, when a star is not still a star, but just like it's being born, that bit still needs more work, right? And JWST will be able to tell us that. Now, this is kind of like my expertise is in this area, and in how exoplanets evolve, how planetary systems form and evolve. And this will help us to know even more about our own solar system, right? And now, something that we couldn't do before, and this is to me, that I'm a planetary scientist, to me, this is the most important part, because now we're going to be able to characterize exoplanets. We couldn't do this before. Like so far, we've been focused for a very long time. We've been detecting exoplanets for like since the 1980s, something like that, right? So we started like the boom in exoplanets, like the boost on exoplanet detection started in 1995. So we've been detecting exoplanets for a very long time, for more than 30 years, right? And the first proposal of an exoplanet was in 1956. So we've been detecting them a lot, and we have detected so far more than 6,000 exoplanets, tons of them, and we have other 5,000 candidates, like tons of them. But something that we haven't been able to do like quite yet is to characterize those exoplanets, to know what they're made of, to know what they have in the atmosphere, to know what chemical elements they have, they don't have, and to know if, for instance, these planets could be like habitable, right? If they could bear life. Right, so that's something important, because we haven't been able to do it well, like so far. And now that we have the JWST, we will be able to, right? And I will tell you later, like how we're gonna do that, right? Because we're already doing it, right? The first, like some preliminary results of the JWST in this area are already coming out. And also in all of these areas, we already have results, right? JWST is already producing science, and very good science, right? And it's paper, like any work that comes from JWST is just a Nature paper, right? Everything goes to Nature, everything goes to the best journals in the world, because most of the JWST science, not all of it, but most of it is the first time that is done. So just a few weeks ago, we observed for the first time we got the spectrum of an exoplanet, right? Something that we never did before. So of course, that's the first time that is done, the first time in the history of humanity, right? So it's an important thing. Now, this is kind of like a description of how these programs, early universe, stars, galaxies, galaxy evolution, exoplanet characterization, all of it, how they fit with the instruments that we have on board JWST, right? So here, for instance, it says all of this is done with a spectroscopy mapping, right? And for that, we use the mid-infrared instrument, so the MIRI, we call it MIRI camera, right? Or the NIRSPEC, the near infrared spectrograph, right? So for all of this, we use these two instruments. So something important, and look, that's why this a spectrograph has the biggest field of view, and it's because this spectrograph can take or can capture a spectra of 200 objects at the same time. So this is able to observe a region and get the spectrum of 200 different objects. Right? That's something that we couldn't do before. This is just way over the limit that we were before. Right? Now, for study the farthest objects either in near infrared, right? Then we need to use the near infrared detectors, right? So we have the near infrared camera, NIRCam, and the near infrared imager and a slitless spectrograph. That's the most complicated one, right? Now, this is my favorite. Why? Because this one is the one that is going to tell us which molecules we have in exoplanet atmospheres. And that's characterization of exoplanets, right? That's something that's the thing that I was telling you before that we weren't able to do, right? Because we didn't have the technology for it. Now, okay, let's go. Now that all the small details about the detectors and all of that is there, let me show you this image, right? This image is a comparison between, the screen there is covering the title, but it's a JWST. Like this is the Hubble and this is the JWST. So this is the same field, right, of Hubble compared to JWST. Now, something interesting here, maybe you already know about this, maybe not, but is that except for the objects that have spikes like this one, right? All of the other points, all of them are galaxies, right? All of them are galaxies. Elliptical galaxies, spiral galaxies, whatever you want, like is there, right? Any type of galaxy is there. Now, what is interesting is what this represents on the sky. This is a tiny part of the sky. So just to to give you a general idea of what this image is like if you hold a grain of sand with your fingers, just like this, and you put it like an arm span, like that all of those galaxies are in that little grain of sand. So this is just a little part of the sky. Some people might think that, oh, okay, that's the whole thing. No, that's just a grain of sand on the sky. All right, just a little bit. So you move your telescope a little bit to a different direction, you have more of that, and more and more and more. Everywhere you point the telescope, you have all of this. All right, so it's just incredible. Right now, look at the level of detail. Right, the level of detail of this. This was the best image that we had before JWST. This is the Hubble. Right, also one of the best instruments that we built and that we put in orbit. But compare like there's just it's completely over the limit. Right, like this is just. This is nothing compared to this, right? Now, look at this information over here. To get this image, we needed 11.3 days of exposure time. So to take this image, these images are called ultra deep images, ultra deep field images, right? So they just put the telescope there and they leave it point there for, in this case, 11.3 days, right? In this case, 12.5 hours. So not even 1 day, not even half a day, right? Well, more than half a day. Yeah. So imagine the difference, right? Like the difference is huge. We were able to get this with JWST only in 12.5 hours, but with Hubble, we needed 11.3 days. Why? Just because of the size of the telescope, right? That's what a big mirror does. By having a big mirror, this is the advantage of a big mirror. And of course, the detectors too, right? The detectors, so the infrared detectors and all of that. So let's keep going. This is another image, very nice. So this is visible light of using the Hubble, right? And this is infrared light using JWST. Now the level of detail is astonishing, right? So you can get like look how you can see the stars. Look here, you can even see them, right? You can see a couple of them, but look here. Why? Because the red light, right, like the infrared light, is more capable of going through dust and clouds. That's why it's important to have an infrared observatory, right? Because what happens is that, let's say that we have a big cloud of dust and gas here, right? Or let's say that the cloud is in between you and me, right? And you are emanating a lot of infrared light. If I'm behind the cloud of dust and gas, and I'm using, let's say, the Hubble or another telescope that doesn't have the detectors that the JWST has, I wouldn't be able to observe you, right? I wouldn't be able to see you, because the light that you're irradiating, the infrared light that you're sending me, is not able to, the telescope is not able to catch that light because of the detectors,
right? Now, because Hubble works in visible light, and visible light is not able to pass through the dust of the cloud, right? Now, the infrared light passes through the dust and gas. But to pass and to be detected, you need the instruments. And that's when JWST comes into play, right? So it says, because we're told that stars forming giant molecular clouds, it is of interest of astronomers to use infrared telescopes, as infrared more easily penetrates dust and gas. That's basically the whole thing. It's pretty simple. Like the principle is, it's not too complicated. Infrared light passes through dust and gas easily, but if you don't have the right detectors, then you won't be able to observe it, right? And JWST has those detectors, and that's why we have more detail now. This is another amazing result from JWST, because if JWST is in orbit, then why would we just using it to observe other things, right? We should be also using it to study our own solar system. There's tons of things of the solar system that we don't know, tons of things. So we also need to use it to like develop more the history of the solar system. Now, here, guys, you have Hubble and you have Hubble and JWST. Now, this is Uranus, right? So you can see that here you can barely see one ring, right? Uranus has 13 rings, right? 11 of them are visible with JWST, and 2 of them were recently discovered when, like, what's that? I think that was Cassini, I think, in a flyby. Yeah, that was a probe that was sent, and it flew around Uranus, and we discovered 2 more rings. So before we thought that there were only 11, but it's actually 13 rings, right? Now, again, the infrared can show us new depths, right? And features that are difficult to see from the ground. From the ground, you will never get this, right? From the ground, you will never get an image like this. Why? Because of the atmosphere, right? That's why space-based telescopes are so important. That's why we need to put more things up there, right? Well, it's going to take a while to put an next JWST or so, or the next one. It's going to take a while because they're expensive, right? But because of this, because of the atmosphere, you will never be able to see something like this, right? You will need something out of the air, right? Now, something else that I'm going to mention in a minute is the orbit of the JWST. The orbit is something super special. It's just what they did with JWST, where they put it is also what makes it special, right? So let's see. This is another one, visible light. Well, actually, no, this is ultraviolet of Hubble, and JWST, again, in infrared light, right? So what you can see here are auroras, right? The auroras. Now, what it says here is that the color highlights the planets stunning auroras, but these colors are actually like artificial, right? They're just to see the features, right? Now, this was taken with the NIRCam, right? And you can see how even this big spot, right, of Jupiter that is so famous, right, is so white here because there's so much light in there, right? And all of it infrared, and then of course you can get it with the JWST, and then basically appears like white, right? But this is infrared and this is ultraviolet, right? Now with the Hubble, you can see some of the auroras, but not quite like that, right? Now this is another thing that is super interesting, right? With the JWST, you can get more detail about the rings and then about the moons, things that we know that are there, right? But we haven't been able to observe like in quite detail. Now this is an amazing comparison, because what you can see here is Europa, right? And Europa is like, it measures across like 3,122 kilometers, right? And that's basically what the Hubble could get, right? But with the JWST, we were able to get to 19.3 kilometers. We were able to see this small moon there, Adrastea, and the other points, there's some points that maybe because of the light you can see them, but there's some like points on the background that are galaxies. You can even see some far away galaxies. Just by observing Jupiter, we can see galaxies behind Jupiter. That's something that we never did before, right? So yeah, they're very, very like tenuous, but they're there. There are some galaxies around, right? And of course, like, look, there is a ring there, right? Now, these are called like Scheffer moons. Like, Scheffer moons are the ones that like move the material around the rings, and that's how the rings like form, right? And here, of course, you can see the ring, right? You can even see the ring here. Here you can see it, right? And then actually you can see a little bit more here. And I think that over there might be another moon, right? So to achieve this sensitivity, to do all of this, like, where do we need to put JWST? Where did they put, right? That's the important thing. So JWST orbits this point. That point is called the second Lagrange point. I'm going to explain what that is. But that point is special because it's super, super far away from Earth. Super far. So for comparison, look where the moon is. Look where the Hubble is. Just in an orbit of 570 kilometers. The moon, an orbit of 384,000 kilometers. This one is 1.5 million kilometers. Very far away. Because of this, James Webb is completely independent. I mean, it can be serviced, right? If something goes wrong, we have to be able to fix it from here. No one's gonna go there. Different to the Hubble, right? When we just launched the Hubble, just 2 years later, when the first images were released, everyone was disappointed. Why? Because there was a big failure in the mirror. And they were like, oh no, like all of this work, and now like these images are nothing, like we don't need this. They had to go there. They went there and they fixed it. Well, because it's just here and it's around the Earth. The Webb doesn't orbit the Earth. It orbits the sun, right? So other telescopes that we have at that point are these ones. Well, these are, some of them are already like decommissioned. For instance, WMAP, right? This was used for cosmology and to trace like the microwave radiation. And these are other telescopes too. This is another one that is also for exoplanets. Now the Webb, James Webb is there, right? And these two too, right? This is also to study the early ages of the universe. All of them are in the L2. All of them are there, right? Now, some people is asking like, oh, is L2 getting crowded? Like, is that position getting crowded? No, like there's a lot of space out there. Like you can still put a lot of things out there. There's tons of space, right? Now, what is L2? Why is this position so special, right? This position is special because of this. Look at that line and look where L2 is. L2 is a point where if you put an instrument there, the sun, the Earth, and also the moon are always behind the instrument, always. Now, the other Lagrange, these are L2, those are called Lagrange points, and are there special because the objects that are at that point, the gravitational forces of the sun, the Earth, and the centrifugal forces produced by the instrument, all of them are in equilibrium. That's what makes it special. So, because they're in equilibrium, just with a bit of effort, you can keep an observatory, the James Webb, in orbit, because all of the forces are in equilibrium. All the points are not. Now, these points, those come from the three-body problem, right? The generalized three-body problem that was solved by Lagrange, right? This guy is super smart, right? So they found 3 points first. At the beginning, there were only 3 points. There was, which ones were? I think it was only L1, L2, and L3. And then Lagrange discovered the other 2, right? So it's actually 5 points. Now, these 3 points, they are not stable points. They're unstable. So that's why the James Webb doesn't dwell in the point. It orbits the point. So it's not that the James Webb is there and it's moving like that. No, James Webb is orbiting the point. You will see a GIF in a minute and it will be more clear. And we do that because if you keep the James Webb just at the point, then the Earth will always be eclipsing the sun. Therefore, the radiation won't get to the solar panels. And therefore, the telescope won't have energy. So that's why we can't keep the telescope at the point, but we need to move the telescope around the point. So at some points, the radiation hits not the instruments, but the solar panels, right? Because the instruments, what you will see in a minute, let's see. So this is kind of like what's going on, right? So you have the Earth, the sun, and you can see that is the James Webb orbiting around L2. It's orbiting around L2, like that. That way, now you will see that, well, before I go to this one, you can see that. But this is charged, I think.
the battery just died. I think I'm gonna use mine. Sorry. So what is important about this position, right, is that it keeps the telescope
always with two sides. So it has a hot side and a cold side, right? So the hot side, of course, is the side pointing towards the sun, right? And that is what keeps the telescope charged and with energy to move around. Now, why is that energy necessary? Because as I said before, this point is not stable. So you need to move, you need to thrust the telescope a little bit in different directions so the orbit keeps constant, right? Because if you don't do that, if you just leave it there, eventually the telescope just will fall to the sun, right? It will just go to the sun. So you need to keep it moving, right? And that's why we need constant energy that comes from the sun, right? Now, let's keep going here. So this is kind of like what happened, what the deployment was, right? From the sun, well, from the Earth all the way to L2, right? And you can see that the first thing that was done, right, was the solar array deployment, first month, right? And then the communications antenna deployment, then the sun shield deployment. Why? Because at this point, from this point onwards, you need energy, right? You need to keep moving the telescope. Now, the secondary mirror deployment and then the primary mirror deployment. So the deployment of the big mirror, that was the last thing that was done. Of course, you couldn't deploy this at the beginning because, well, close to the Earth, you have all the things, anything could hit the telescope. So you have to protect the main mirror, which is the most important part of the telescope. You have to protect that right to the end, right? That's the last thing you do. Now, here you can see more clearly, right, where the sun is located, the Earth, and you can see that the instruments, right, and the mirror are always on the cold side of the telescope. So this is the sun shield, right, that big diamond, right, like this. And that one is always facing the sun. So you have a hot side and a cold side. On the cold side, you have the cameras, you have the instruments, you have the electronics, all the bits that can like absorb heat and then irradiate it, right? And on the other side, you have the solar panels, right? You have the sun shield and that. Now, it's really, really particular because is the difference between the two sides, the hot side and the cold side, is just like ridiculous. Like the temperature on the hot side is about like more than 80 degrees, more than 80 Celsius degrees. The temperature on the other side is minus 233. So imagine that difference, right? So you can freeze something on one side and you can boil an egg on the other side, right? Now, here, this is telling you what the temperatures are on hot side and cold side, right? So the temperature gradient is huge. Now, these are the components that are on each side, right? So the hot side, the cold side, right? So on the cold side, you have all of the mirrors, of course, right? And the integrated science instrument module. And on this side, well, you have the sun shield and you have the antennas and all the things that are really not affected by the heat, right? What you don't want is the heat hitting the detectors, right? You don't want that. It's actually, if something, if like that's what that this has to do with this part, right? If you deploy the instruments and the mirrors like way before the protection of the sun shield, then you can easily melt everything, right? If the heat of the sun arrives to the instruments, it could melt the instruments. It could just destroy them completely. And then you will have just garbage arriving to L2, right? So that's why that's the last thing we do. Now, there's something special about JWST, that is that because of the orbit, because of the motion that the JWST does, JWST is able to observe 35 to 40%, right? It's kind of like an annulus of the sky. That doesn't mean that that is the only thing that it will observe. No, because as it's doing this around L2, it's also moving around the sun. So that annulus that it's observing keeps moving. So if you start like observing this annulus of the universe and you keep moving, then you're observing a different annulus because the James Webb is moving around the sun, right? So in 6 months, JWST is able to cover the whole sky, right? It's able to cover the whole thing. So, but for that, you need 6 months, right? So it's basically the design of the orbit, right? So this is kind of like the axis that you have, right? So it says this is the colors represent the maximum continuous visibility duration, right? And the CV set is the continuous view in sun. So there is some areas that are continuously observed by the JWST that they have access all the time, right? So are only these points, right? But the annulus keeps changing. So every 6 months you have observed the whole sky, right? So the sky, well, the James Webb is going to be in orbit for, let's say, 12, 15 years. So we're going to observe the sky a lot of times, right? The whole universe, multiple times, right? And that's something very, very special. Now, this is just a comparison of like the evolution of the of infrared space telescopes. So this is kind of like one of the first ones, right? WISE. Look at the detail, right? Look here and then look JWST, right? This was the Spitzer, right? This is not even Hubble, right? Remember that Hubble doesn't have access to the infrared part of the spectrum, right? So, but the Spitzer has, right? This is the one that also had like a bit of an overlap with JWST, right? And this was the best infrared telescope that we have. Like before JWST, this was the best that we could get in the infrared. And this is not even like the near infrared. This is kind of like after the mid infrared, right? So, but look the difference, right? The difference is astonishing, right? It's really, really, like really good, the things that we can do with the JWST, right? Now, this is another comparison. This is one of also some of the first images that were released by JWST. And you can see here, this is an observation of the Large Magellanic Cloud, right? Using one of the instruments, the MIRI camera, like the mid-infrared camera or the mid-infrared instrument, right? And what you can see here, like as you describe, like the puffiness that surrounds the stars is the cloud from carbon-rich organic molecules, right? So those are all of the things that now we can observe with the JWST, right? We can get to that level of detail, like this, for instance. Here before, what color are you going to observe there, right? There's nothing there, right? Like you can't get anything from that, right? But now you can, right? You can see all of like how the gas is distributed, right? You can study the gas density, the dust density, and all of that has to do also with planet formation, with planet evolution, with the star formation. So it's not just observing the stars and this little and the pretty clouds that are around, right? It's the consequences, right? The consequences that this has, right? The consequences of being able to observe gas, to observe dust, right? The study the evolution of this gas and dust, because all that gas and dust eventually can create stars, can create planets, right? So this is a really, really nice tool and a really nice like way that we have now to observe the universe, right? This is another comparison again, JWST, Hubble, and this is something that we call the Helix like nebula. Hubble here is the same image, is the same object, right? Just the level of detail again, like with the JWST is way better, right? Now, getting into topic of like what we can do or what we already doing with the JWST, right? I'm going to start with the exoplanet part. So this is something that we've been doing this for a while, not for characterizing, but for detecting exoplanets, right? So this is called it's kind of like a signal that the exoplanet sent, right? And it's because of the interactions, the gravitational interactions that exist, right, between a planet and a star, right? So when you are able to observe a star that is in an edge-on orbit, this is called an edge-on orbit. It's just that moves in front of the star. That's all it means, right? So by studying how the star like wobbles, right, you can see that the star moves a little bit, right? And detecting the spectrum of the star, you can know, right, that a planet is there, and you can predict the size of the planet. You can predict like, oh, for that star, for those lines to move that much, the planet has to be, let's say, 2 masses of Jupiter or 10 masses of Jupiter, right? You can tell the mass of the planet, but that's all you can tell. You can't tell more than that. The only thing you can tell there is, oh, there is a planet there, and it has to have this mass, but that's it. You don't know what the atmosphere is made of. You don't know what elements are there, what molecules are there. You have no idea, because this is just a detection method, right? Not a characterization method. But now with JWST, right, we're able to do this, right? Something that we couldn't do before. This is what we call transit spectroscopy, right? So transit spectroscopy is studying the light that comes from the star, right, but that passes through the atmosphere. When you're able to do that, then for instance, a planet that has a small atmosphere, let's say this light there is not passing through the atmosphere, so you don't detect anything. You don't detect any elements because the light is coming straight from the star to you, to the detector. So you're not able to tell the absorption of the atmosphere, right? But if you have the light going through the atmosphere, then you have absorption of light. You have light absorption, right? And then you are able to tell, okay, for this absorption to happen, this atmosphere has to have water, maybe water vapor, and carbon dioxide, carbon monoxide, well, etc., right? Any element, right? Now, these planets, and something that we're focusing on right now, is in planets that are really, really close to the star. Why? Because these planets, something that we call hot Jupiters, the hot Jupiters are planets like Jupiter, but orbiting even closer than Mercury around the sun. So these are planets that have orbits of 5 days, 4 days. Imagine having a planet like Jupiter, that is the biggest planet in the solar system, but orbiting just in 4 days or 3 days. The effects that you have on the star, not only like gravitationally speaking, but also like in terms of atmospheres is really interesting, because being that close from the star, you have these planets that sometimes we call puffy planets, right? Because the atmospheres are super inflated, right? These planets, the atmosphere just goes so for so long that then you're able to do this, right? So that's why now we're focusing on the hot Jupiters, because by studying the hot Jupiters, we can improve the transit spectroscopy technique. And then we can start studying other smaller planets, like rocky planets, because the goal is that, right? What we have in mind is to characterize planets that are similar to the Earth, right? That are similar to our planet. And then moving into the habitability part, right? So something like a bit of more explanation about how this technique works is that if you have the planet orbiting in front of the star, right? And if you study different parts of the spectrum, like different lights, right? Different colors, then you have different absorption. And then you can tell like which elements or molecules are in the atmosphere just by studying in multiple colors the absorption of the light, right? So it says during a transit, some of the starlight is eclipsed, right? Like this is an eclipse. This is what we call a transit or just an eclipse, right? And some of the light is transmitted through the planet's atmosphere. So now this is one of the first results, right? This is one of the first results of JWST. And here you can see how they took the light curve. This is something we call light curve, just like how we study the light from a star. And you can tell that this light, it says planet's atmosphere blocks less of this color. Yeah, less because you have more flux. So the vertical axis is the flux of the star. If you have no planet, this flux should be always the same. If nothing is passing in front of the star, you should always detect the same flux, right? But if something is passing in front, then that's when you have an eclipse, right? But studying different colors, you can see that some of the light is more absorbed in other colors than in these ones, right? So the planet's atmosphere in this case, for instance, blocks more of the color because of the absorption of CO2, right? And there is less absorption. So by studying different colors, we're able to tell what elements are there. Now, in this planet, which is WASP-39b, this planet was already known. It's not that JWST discovered this planet. No, we already knew this planet. It's just that we couldn't do this characterization. We couldn't study the atmosphere at all. Now we can. So here, this is again another result from JWST, right? Using the near spec. And here is the detection. This is a Nature paper. This is one of the first results, big results of JWST, was the detection of this in an exoplanet atmosphere, right? Something that like we couldn't do. Now, this is a complete, right, spectrum of the planet. And here's the detection of many, like molecules, right? And this is the first time that it was done, right? Being able to detect this in an exoplanet atmosphere, right? So you have water, you have carbon monoxide, carbon dioxide, you have what else? Sulfur dioxide, right? Now, bear in mind that this is a giant planet, right? This is a hot Jupiter. What I was telling you before, this is just a hot planet, giant like Jupiter, orbiting super close to the star. And that's why it's easier to do this, because they have big atmospheres. Planets like the Earth, rocky planets, small planets, don't have those big atmospheres. So doing this type of a study in rocky planets it's going to be more complicated, but it's going to be super interesting once that happens, because we're moving towards that. All of this is just to study planets like ours, just to study planets that are could be like the Earth, right? Like this one, for instance. So this is a system that we detected like years ago, and is one of the most similar systems to our solar system, right? It's called TRAPPIST-1, and it's a planetary system that has 1, 2, 3, 4, 5, 6, 7 planets. Our system has 8, right? Now, what is interesting here, right, is that 1, 2, and 3 of those planets are inside the habitability zone. The green area is the area where where liquid water can exist, where you can have liquid water, right? So these 3 planets, E, F, and G, those 3, in theory, could have liquid water. So that's why we're interested in doing these studies in planets like these ones, because then we will be able to tell if we have organic molecules in the atmosphere, right? We will be able to tell if there is interesting stuff, right? We're moving towards the detection of something that we call biosignatures, right? Or technosignatures. That's a bit more like this, it's new, and there's people proposing, right? Like what kind of thing you will detect in an atmosphere in a planet that has a, let's say, like industry, right? Or that has farms, right? There is a paper that just came out a few weeks ago that is called like exofarms, right? So it's like detecting like the atmosphere, how to detect what molecules you will find in a planet where there is farming, right? So that kind of thing, in the future, we could do that with JWST, totally. If we improve this technique, we could do that. Another thing that we could do is this, right? This is another interesting part, and it's the study of protoplanetary disks, right? So far, like we've done a lot of study in protoplanetary disks, but with JWST, we will be able to get more in detail, right? This is a planet, and this is a ring around the planet, but that's not the protoplanetary disk. This is the protoplanetary disk. So that thing there is the formation of a moon, right? What you have here, that is the formation of a moon, right? The formation of the first moon. Now, we haven't confirmed it yet, but with JWST, we could. We haven't detected any extrasolar moons so far. I told you before, we have detected more than 6,000 exoplanets, tons of them, and we have other 5,000 candidates, but not a single moon. We haven't been able to observe a moon. Why? Because detecting an exoplanet is already difficult, because planets are tiny compared to the stars. Stars are huge and planets are small. Right? Now imagine a moon. Moon is basically from Earth, from ground-based telescope, is undetectable. We can't observe a moon, an extrasolar moon, with telescopes that are here on Earth. But with a telescope that is out of the Earth, like in space, you could. And JWST could totally observe these extrasolar moons, right? Now, these are other results from JWST. And for instance, here, this is something that before we thought that this is the galaxy cluster SMAX 0723. And before we thought that these two arcs here, we thought that they were different galaxies, right? For a while, we thought that they were different galaxies. With the JWST, we actually proved that they are the same galaxy, that they're part of the same galaxy, right? How? By studying the spectrum. By studying the spectrum of this bit and this bit, right, we were able to prove that they're actually the same, right? And this is the kind of thing that we can do now with JWST. And this allows us to go, like, to know more about the history of the universe, right? How the universe formed, how the universe is evolving, and how it evolved years ago, right? This is another thing, right? The Webb spectrum showcases galaxies' composition, right? So now we are able to trace the chemical history of the galaxies. Now we're able to tell like where there is accumulation of different molecules or different chemical elements, right? Now, for instance, this is a galaxy that is 13.1 billion years. We never did these observations before, right? This is a galaxy that is 13.1 billion years old, right? And we were able to tell the composition of the galaxy, right? All of the chemical elements of the galaxy. So you can, as you can notice in all the results that I'm showing you, everything is about the spectrum. Everything is about molecules, chemical elements, because that's what we couldn't do before. Detecting galaxies, detecting planets, all of that, that was already done. This is what is new. is detecting the composition, right? Detecting what elements, what molecules we have there. That's the thing that we didn't have access to before, right? This is Webb spectra identify galaxies in the very early universe. So these are different galaxies at different ages, right? So this is a 11.3 billion years old galaxy, 12.6 billion years old, 13 billion years old, and 13.1. This one is this one than before, right? And these are in the image. You remember the image that I showed you before, in the comparison between Hubble and the James Webb. The first image released by the JWST is this one here. In this image, like tons of studies have been already done in that image. Such a simple thing, but there's a lot of people working on this, just studying the spectrum of different points in that image. This is one of those examples, right? Where you have in that single image, you have 1, 2, 3, and 4 here, and you're able to tell the composition of all of those galaxies, right? And that's important because then if you're able to trace the composition of all of those galaxies, then you're able to tell the type of stars that they could form, the type of stars that you can have in different parts of the universe, and so on, right? So this goes very deep into the evolution of the universe, right? Knowing all of these things will allow us to know more about our own galaxy, right? Now, just to start like concluding with the talk, right? To mention some issues with the JWST, this was the big problem that I mentioned you before. There was a big impact of a meteoroid, just like months after starting. So everything went perfect for the first month, second month, 6 months, boom, they opened the mirror and boom, the meteor arrives. Why didn't it arrive before? Well, I don't know. This mirror hit there and it all like, it's the impact of this, like remember, like the impact of this is just the velocity, like the speed of a meteoroid is just, it just goes through, right? It's not like it's gonna hit and break now. Just opens hole completely, right? It just like a bullet, right? Now, these are micrometeoroid impacts. This is not, we're not talking here about like a softball, right? Like, no, like here, this is just tiny, right? Now, this is not very serious. And this was actually predicted before putting JWST in orbit. They were expecting this. They said like, oh yeah, the JWST is gonna be hit at least once a month by a meteor, like by a micrometeoroid. That's gonna happen. At least once a month is gonna happen. But they didn't expect this big, right? So far, it's only happened once. That hasn't happened again. The damage wasn't that serious, wasn't that bad, right? And here it looks very bad, right? But it's not like the science of the instrument and everything wasn't affected like badly, but it's something to be like aware of, right? Like it could keep happening, and then actually trying to think of and like, oh, coming up with ideas to fix this or maybe to prevent this from happening in the future, right? So yeah. Another problem, and well, these are just, I think these are just problems that happen with any instrument, is also communication delays, right, with instruments. This happened also like after the 6 months where the telescope was ready to observe. 1 month later, they couldn't connect to the cameras. They were like, oh no, like they couldn't connect, right? And that's kind of curious, because one of the reasons why they put JWST at the point that I showed you before, at that special orbit, is because it's very far from Earth to prevent the heat from Earth to reach the telescope, but it's still close to communicate with the Earth. It's still close to send images and data, right? So far enough to prevent the heat, but it's still close to send the data, right? So it's expected like we should be able to send the data, and they were like for days trying to fix the error, but at the end, for this one was possibly produced by a galactic cosmic ray. The first glitch, this is the first glitch, second glitch. So the first glitch was produced by a galactic cosmic ray. That was like, they conclude at least there were no damage, permanent damage or anything, right? And this one here was more serious, and this was produced by like the friction between the some internal components of the instrument. It seems that the friction produced like a bit of heat, and that was producing like errors with the communication with this camera. But at the end, they could fix it remotely. Well, they have to, right? Like how they're not going to send anyone there, right? So now, this is what I mentioned at the beginning, right? So about the name of the JWST. So that's another issue, that we need to change the name of the telescope, right? Like it's not really like, there's some problems, and is that there's been some investigation, and NASA says that it's not like that. Well, of course, they're going to cover it, right? Is that in this person, James Webb, right? He was a former in the Apollo era, right, of NASA. And at that time, well, and not only he, but many people, right, were like promoting like policies and things against people from the LGBT community, right? And just for their condition, right, whatever it is, they will fire them, right? And this is, well, like, this is not acceptable, right? Like this can happen. And now what is interesting about this is that they don't think about the consequences, right? Like if you put like a name of that to a telescope, and in astronomy, where is astronomers, the people that are using the telescope, right? There's a lot of people from this community, right? Like tons, and they can't, like, and they won't, right, feel okay like applying for fellowships or applying for work or applying for different jobs to use this telescope if that has the name of a person that in the past, right, was against them, right, just for that. So I think there is like a real reason, right, to promote the name of change the name of the telescope. Some people are promoting to change it to just Webb Space Telescope, removing the James. Like the same with the Hubble. Like the Hubble is not Edwin Hubble Space Telescope; it's just the Hubble Space Telescope. So they're trying to make it easy for NASA, but even that NASA doesn't want it. They said that they're not going to change it, and so yeah, there's a big movement around that. So that's it. Just saying that we need more equity and diversity in the world, right? And in sciences and everything. And that's something that right now there's a big movement around that to change the name of this telescope because of this, right? Because at the end, anyone can be a scientist, and it's important to promote this for anyone, right? So with that, I want to finish, and yeah, just leave it at that. Thank you.
Well, that was just fantastic. And we have to reward you with some wine. Thank you very much.
Thank you.
Now, because everyone's in the room, you get first crack at some questions here, and then we'll go and see if there's any online. So, you've got a question?
Yeah.
I knew it would be Steve.
I had several questions. First question, from the start of your talk, you mentioned the change from one instrument to the other. How is that done? Is that a mechanical movement from,
Yeah,
isn't that going? I mean, could they use a beam splitter or something or other else to?
I think they just use something to cover the instruments. So like you have your instruments there, right? And like you want to avoid as much as possible, right, moving things around in the telescope, right? So it's easier if you just have them completely available, but you just cover them, or you just have like you uncover the instrument that you want to use, right? So if you're not using two of the cameras, well, you just like move something on top, and then you don't have anything there, right? If you want the four of them detecting, well, you have the four of them uncovered, right? So it's just a matter of like just putting like a sheet on top of it, right? Like just covering things, right? So it's not too like that helps with also with like avoiding the heating of the telescope, right? Remember, like anything, the electronics will heat, and the heating will affect the observation. So the way that JWST does it is just by not moving things around, like just uncovering and uncovering things. So
Anything they don't need, they switch off.
Yeah, you could switch off too. Yeah, at the end, every single part of the telescope, like absolutely everything, can be controlled remotely. Right, everything can be moved. Everything can be done from here, from the control center on Earth. So yeah, at the end, if there's anything that you need to switch off, yeah, you can do it too. Yeah.
I was going to ask about what other Lagrange points.
Yep.
I guess so L3 would be out because you couldn't communicate with Earth, right?
Yeah, let's go by there.
The wrong side of Earth.
Like that one, yeah. So yeah, so the thing is that, for instance, if you can't put anything, well, actually, you can. There is something in L1. We have SOHO in L1. We have the solar and heliospheric observatory. We have an observatory there, but it's to observe the sun, right? Because otherwise, like it would melt, right? So yeah, we have there Soho, right? And we haven't put like so far we haven't been able to find any like useful application for L5 and L4. For this one, there are some proposals to put like also like another solar observatory there, but for these ones, no, not yet. We haven't put anything on these points. But interestingly, these L4 and L5, those are stable points.
Yeah.
So in these points, we have accumulation of asteroids. So I don't know if you have heard about this population of asteroids that is called the Trojans. So Trojans, most of the Trojans in the solar system are accumulated in L4 or L5, but not of the Sun-Earth system, but the Sun-Jupiter system. So we have most of the asteroids are accumulated in these points, right, in Jupiter, right, in the orbit of Jupiter, right? But because of that, because these are stable points, that's why all of the asteroids end up there, and that's why there is no reason to put like an observatory there. Imagine putting an observatory there surrounded by rocks. It's not really a good idea. So we haven't been able like to find like something useful to do with these points, right? So, and L1, yeah, solar observatories, but L2 is the way to go if you want to keep an observatory or a telescope. You want to keep it cold, that's where you should put it, because it's always behind the sun, the earth, and in this case, also behind the moon.
Isn't there another planet hiding at L3?
That's one of the theories, right? Planet 9, there's like Planet X, actually, they call it, right? That's what they think that is in L3, right?
Some people.
Yeah, the flat earth. So actually, like I'm working like I just started like a project where I'm studying like not with a star, but you have, because the Lagrange points exist for every pair of bodies, right? So if you have a giant planet and you have a moon, that system also has Lagrange points, right? Also has L1, L2, L3, L4, 5. So what I'm trying to do is to do simulations of having a planet, having a moon, and what happens if that moon has a system, right, of moons or small little sub-moons, we call them, right, that they could end up or migrate to L4 and L5, right? But what I'm interested in studying is that seeing if instead of putting the bodies around the moon, what if you put them already in L4 and L5 and see if with time they end up going towards the moon, right? So these 2 points, L4 and L5, are very interesting, but not for observatories, or at least not now. Yeah.
Another question was, so we've got the secondary mirror that is then doing it. How are you splitting that image to get to the different sensors, or is it only one sensor operating the time?
Yeah, I think they use an splitter. Like, it's just that, as I said before, you can have all of them observing, that you can have 2, 3, or 4 of them observing, or you can only have one, right? So you don't really need to split the light, right? You just need to like kind of like distribute it like in a smart way, just by exposing the instrument that you want, or just covering it with something, right? Like, so yeah, I don't think you need to split the light really. Yeah.
I thought it was a good question.
Yep.
Took me a while to think of a good one. So you showed a slide, it was about slide 40. So just because 2 things look the same doesn't mean they are the same. So you're thinking about geochemistry on Earth, for example, if something is 40% quartz and 60% feldspar, it could be a granite, or it could be sandstone made from granite. So when you're seeing that you've got a very similar spectrum, this one. Does that really mean they're the same, or does it mean they're similar? And well, how unique are the spectra?
They like, well, you didn't put the details here, yeah, but there is a kind of like a percentage, right, of saying that they're similar or not, right? Like the percentage is very high, it's more like than 85%, because the spectrums are very, very similar, right? But yeah, you're right. Like they need to, like, actually right now there is like 2 groups from the European Space Agency that are working on this, and it's because it's still, even if the spectrums are the same, they could look the same. So they're observing this further, right? Like this being studied. Like so far, they confirm that the 2 arcs are the same galaxy, but it could be possible that in a future study, they could say like that few like new observations reveal maybe a new part of the spectrum. Because if you see here, right, the wavelength of this just goes in microns. This just goes from, let's say, 1.1 to 1.3. So it could be that in this part of the spectrum, they are very similar. But if you observe with another instrument that covers a different part of the spectrum, maybe you can reveal other features, right? And if you're able to reveal maybe another feature, not in 1.3, but let's say in 5 microns, you're able to reveal something that is here, but it's not here, then that will be like an errata for this result, right? Saying like, oh no, like actually they're different because, but so far they haven't been like, the spectrums are very, very similar. Like, so there's a very, like, yeah, that's true, yeah. Now you actually can see, right? Like this is, you see how they arc. So there is a bit of like lensing too. So yeah, there's a lot of things going on.
But are these like some of the most common? Are they going to be some of the most common things?
Yeah.
As well?
This is a bit more in my field.
Yeah.
I said that there'd be an extra bit of information about not just the spectra, but exactly where those spectral lines are, which would tell you about the relative velocity between us and that galaxy. Which that would be a really telltale signature. But yes, there would be a massive object between us and that, because that is gravitational lensing. Yeah. So it's almost like an optical illusion. What you're seeing there, those two arcs are it's
Migration.
yeah, it's more like a mirage. It's an effect of general. Yeah. Something, well, it's probably something bright. It's probably that big, huge cloud right there. But yeah, some.
Yeah, that's probably another galaxy. This is an elliptical
It
galaxy.
could be, yeah. It could.
That's an elliptical
It's
galaxy.
usually a foreground large elliptical galaxy that bends light from more distant galaxies behind, but those two have what's called the same redshift, which is the same precessional velocity. And that's another signature that would help us with not just the
Not just the
portion of
spectrum.
the elements, but then also the velocity.
That makes sense. Yeah. Other
I have a
information.
Same doubt on top of that. So what if there is a galaxy behind that and it's overshadowing the front galaxy, but obviously we can see the galaxy behind. But how can you know the signal is coming from, or the spectrum you're getting from the galaxy on the front or from the back, or is it fixed?
Pretty hard to tell.
It's super.
You just pointed out the difficulty.
You know, that can actually happen, right? Because if there's a galaxy behind, we can't really see, but it is super emitting than the galaxy in the front.
Yeah,
Then
yeah.
we can get signals from that galaxy actually, but we will never know.
We're getting into
you-
geophysics
yeah.
now.
What you can try to do is actually something that the JWST can do is also a new thing that we haven't done is coronographic spectroscopy. Right, so you can cover that, right? So you could cover parts of the image or parts of the data, right, and then subtract the two spectrums, right? So you can use like subtraction of a spectrum by using like coronography spectroscopy, but that's new. That's something that is still like is being done, right? It's not a lot of results on that part, but yeah, but you can there is ways to get rid of the background and then tell what information is from the forward, like from the galaxy or the object on the front, right? On something that is behind. So there is ways to do that. Yeah.
I've got another question. So what sort of spectra would you expect from planets that are made predominantly of platinum and gold?
What's